Hello friends, the topic for today is vectored and non-vectored interrupts of 8085. This video I am updating in English. I already updated the version in Hindi. Today we'll have the video in English. Now interrupt is a facility provided by the microprocessor to communicate with the outside environment, and the microprocessor can divert its operation based on the priority. Now an interrupt process where an external device get an attention of the microprocessor. When the microprocessor receives an interrupt signal, it suspends its currently executing program and jumps to an interrupt service routine or ISR to respond to the incoming interrupt. There are two different ways of redirecting the execution of ISR depending on whether the interrupt is vectored or non-vectored. In today's video, we'll discuss the processing of vectored and non-vectored interrupts of 8085. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon so that you get notifications for our future video. The topic for today is vectored and non-vectored interrupts of 8085. Let us start with the introduction. Now, as we already said, that interrupt is a facility provided by microprocessor to communicate with the outside environment. That means whenever any peripheral device wants to communicate with the microprocessor, then the microprocessor is providing lines or pins for communication, and they are nothing but the interrupt pins. Now microprocessor will be generally busy in executing the programs, so the microprocessor can divert its operation based on the priority of the interrupts. Interrupt can be used for various applications in different environment. For example, they can be used for processing keys pressed, that is for keyboard, or they can be used for getting signal converted from analog to digital. So the process starts from a IO device, and it is a synchronous type of data transfer. See, here you can see in the figure, we have the 8085 microprocessor connected with the IO device, and the connection will have the address bus, and then these two signals interrupt request, so that will be coming from the IO device to the 8085 microprocessor on this line INTR, and then we have the interrupt acknowledgement signal INTA bar, which is active low, so that will go from 8085 to the IO device. So the microprocessor can initiate the data transfer after getting an interrupt signal from the IO device. So the IO device will send the interrupt signal, and then the microprocessor will initiate the data transfer. So now this pin, it will check, and if it is, say, in the every machine cycle, it will check this pin INTR, and when this signal is present, it will suspend its present operation and provide services to the interrupt request by executing a interrupt service routine ISR. That is the general procedure, and for that we need the vector address of the interrupt. Let us see how we can do it. So here, this is the general execution of interrupt. So when microprocessor receives an interrupt signal, it suspends the correctly executing program and jumps to the interrupt service routine to respond to the incoming interrupt. So here you can see the microprocessor will be executing the main program, and whenever it receives an interrupt request, at this point it is receiving the interrupt request. So when it receives the interrupt request, it will go to the interrupt service routine or ISR. Then at the end of the interrupt service routine or ISR, there is a return instruction. So it will return back to the main program. You can see again, and it will start executing the main program. Then it will continue execution of the main program, and again when it receives interrupt request, again it will go to the interrupt service routine ISR. So once that is completed, again it will return back to the main program. So this will be the general procedure for the interrupt execution, and each interrupt will have its own ISR. Now here there are two different ways of redirecting the execution to the ISR depending on whether the interrupt is vectored or non-vectored. So in vectored interrupt, the address of the ISR is already known to the microprocessor, because there is a interrupt vector table which will have the address of the interrupt. Then in case of non-vector interrupt, the IO device will have to supply the address of the subroutine ISR to the microprocessor, and that will be done with the help of the data bus, and the timing diagram for that will be used. We'll see the details of that later on. Then let us come to the basic definition of vectored and non-vectored interrupt. Okay. Whenever interrupt request is activated, the microprocessor control logic executes an ideal machine cycle, and during this cycle it generates the starting address of the interrupt service routine. So the starting address of the interrupt service routine or ISR will be generated during this cycle. Now these addresses, they are fixed for different interrupts, and the address of the ISR is called as the vector address, because that is actually a 16-bit address that will be from where the interrupt will be executing the ISR. That's why it is called as the vector address. And interrupts which these vector addresses are present, they are called as the vectored interrupt. Now 8085, there are total 5 interrupts. Out of that, 4 are vectored interrupts. That is trap, RST 7.5, RST 6.5 and RST 5.5. These are the 4 vectored interrupts because they have fixed address of the ISR in the interrupt vector table. Then the non-vectored interrupt, there is no vector address for the interrupt, and so the interrupting device should supply the address of the ISR to be executed in response to the interrupt. Only one interrupt is there, that is non-vector, that is INTR. So the INTR interrupt will supply the address with the help of the interrupt acknowledgement signal, INTA bar, using the hardware. We'll see the details. Then let us first see the interrupt vectors and vector table. Say, when we say interrupt vector, it is nothing but a pointer in which the ISR routine is stored in memory. So all interrupts vector or otherwise, are mapped onto the memory area called as the interrupt vector table. So this is generally located in the memory page 0, 0, 0, hexadecimal it is 0, 0. So the address for that will be 0, 0, 0, 0 to 0, 0 FF. And this interrupt vector table will hold the vectors that redirect microprocessor to the right place when the interrupt arrives or occurs. So you can see this table here, the interrupt and the vector address is given. For RST 7.5 it is 003C, 6.5 0034, 5.5 it is 002C, and for trap it is 0024. And these addresses, they are fixed for these interrupts. We can't change these addresses. So whenever we want to use these interrupts, at that time we'll have to make use of this address vector. Then here, as we have already said, there are 4 vector interrupts: trap, RST, 7.5, 6.5 and 5.5. Out of this, trap is non-masked, it cannot be masked, and generally it will be used for the emergency condition such as power failure. And the other 3 interrupts, they are maskable vector interrupts. They can be masked, and the processing of these interrupts will be carried out with the help of these steps. Now in the first step, we should enable the interrupt using the EI instruction. So EI instruction is used for enabling the interrupt. Then the 8085 checks for an interrupt during the execution of every instruction. Now if interrupt occurs and the interrupt is enabled using the interrupt mask, the microprocessor will complete the execution of the current instruction and then reset the interrupt flip-flop. Now this interrupt flip-flop, this we have studied in the interrupt structure. You can refer to the interrupt structure. There we have the interrupt flip-flop. So with the help of enable instruction, we'll set the interrupt flip-flop and then it will be reset whenever any interrupt occurs. Then let us go to the next step, that is 4th step. So here the microprocessor executes the call instruction which sends the execution to the appropriate location in the interrupt vector table. So depending on the interrupt, it will send it to the particular location in the interrupt vector. And we have seen the different locations. So when the microprocessor executes call instruction, it saves the address of the next instruction to be executed on the stack, because when it goes for execution of the ISR, it has to return back after that. That's why it will save the address of the next instruction on the stack. On the stack means in the stack memory with the help of the stack pointer SP. Then the microprocessor jumps to the specific service routine, that is the ISR, interrupt service routine, and it must include the instruction EI to re-enable the interrupt process. So again the ISR will also have the EI instruction to re-enable the interrupt, because whenever if the microprocessor needs another instruction interrupt, at that time the interrupt should be enabled. So at the end of the service routine, we have the return instruction. So that will return the execution to where the program was interrupted. That is the main program. Then let us discuss the non-vectored interrupt. So here we'll concentrate only on the INTR interrupt, because that is only the non-vector interrupt. So again, the first step is the interrupt process should be enabled using the EI instruction. So it has to be enabled with the help of the EI instruction. Then the 8085 will check the interrupt during execution of every instruction, and if it finds that INTR is high, it will complete the current instruction and disable the interrupt and send INTA, interrupt acknowledge signal, to the device that interrupted. So this signal INTA, this is a active low signal, so actually it will be INTA bar will go. Then INTA allows the IO device to send a RST instruction through the data bus. Now you have to understand this. This RST instruction is nothing but the restart instruction, that is for giving the address or vector address to the interrupting device. So after receiving the INT signal, the microprocessor saves the memory location of the next instruction on the stack similar to the previous one, and program is transferred to the call location, that is the ISR call specified by the RST instruction. So this RST instruction will give the address, because it's a non-vectored interrupt, it has no address of its own. That's why that will be given by the RST, and the RST instruction will give this address during this INTA this signal with the help of this INTA interrupt acknowledge. Let us see how it will be given. Then the next step is microprocessor performs the interrupt service routine, and again it should have the EI instruction to enable further interrupt within the program, and it will also have the return instruction, RET instruction, at the end of ISR to allow the microprocessor to retrieve the return address from the stack, and the program will be transferred back to the location from where it was. So it will go back to the main program. So this is the general process of the non-vectored interrupt. Then let us see how we can say, give the address with the help of the restart instruction. Now 8085, it has 8 restart instruction, RST0 to RST7, and this will be used to send the execution of predetermined hardwired memory location. So here the address of the interrupt will be generated with the help of hardware. So now this is the RST instruction, and it will have the hexadecimal code. This is the code of the instruction, and the vector address, the RST0, it will be 0000, RST1 it will be 0008, and RST2 0010. Now if you look at this part, it is nothing but simply where if you take RST n and simply multiply it by 8, you will get this address. The RST1, the address is 0008, then RST2, it is 16, but in hexadecimal 16 is 0010. That's why you will get 10. Then RST3, the address for this will be 24. In hexadecimal it is 18. Then RST4 will get 20. Then RST5 it will be 0028. RST6 it will be 0030. Now RST6, the address will be, if you are multiplying by 8, you will get 48. So in hexadecimal 48 is equivalent to 0030, and last RST7 the address is 0038, and these are the hexadecimal codes for these instructions which are to be used for generating the a particular address. Say for RST5 this code is EF. We'll be using this code for our next process. First, let us understand the restart sequence. Now, restart sequence, it is made up of 3 machine cycles. Say we'll have the first machine cycle, and then second machine cycle, and third machine. So these machine cycles are nothing but the timing diagram. With respect to timing diagram, we'll have to see the machine cycle. In the first machine cycle, the microprocessor will send the INTA. So this INTA is an active low signal. So when this INTA signal, or call it as INTA bar signal, reads the is given at that time, it will read the data lines expecting to receive from the interrupting device. That is the opcode of the specific RST instruction. So that will be read on the data lines. Say RST5 the opcode is EF, so that will be coming on the data lines. And during the second and third machine cycle, the 16-bit address of the next instruction is saved on the stack. That is for returning back to the main program. And then the microprocessor will jump to the address associated with the specified RST. That is the address of the ISR, interrupt service routine. Let us see the timing diagram first, and then we'll see how we can generate the particular address. So here in this timing diagram, this is the timing diagram for the restart instruction. We have the clock, then this is machine cycle 1, machine cycle 2, and this is machine cycle 3. Machine cycle 1 has got 6 T states, machine cycle 2 has 3 T states, and machine cycle 3 it has again 3 T states. So this is the clock, and these are the higher order address lines. So during machine cycle 1, it will have the program counter higher order byte, and these are the lower order address bus and the data bus multiplexed. So it will have the program counter lower byte, and then here it will have the RST instruction. So RST instruction will be here, and during the machine cycle 2 and 3 will have the opcode. So the opcode will come on the data lines. So here PCH, that is it will have the higher order things, higher order address will come on this PCH, and it will be loaded into PCH, and this lower order address D0 to D7 will be coming in the machine cycle 3. Then this ALE signal there is for fetching the address. This is address latch enable, and this is the INTR signal, it is high, and INTA bar, this signal it is going low, it is active here. So when it is low, at that time only we have the RST code, and then here we have the read bar and write bar. So the read signal is high, whereas the write signal will be taking this address from here when it goes low. And these are the signals IOM bar, that is for the and the status lines S1 and S0. So it will have the status as per the say whether it is the page cycle or the other cycles. So here it will be 001 001, that will be the state. So this IOM bar will be 0, then S1 and S0, that will be 0, and this is the phase cycle, that's why it will be 1 1 0. So as you can see here, if anything is left, say the address line, higher order address lines, this is the higher order address line, that is from the program counter, and then will carry the stack pointer SP-1 and SP-2, that is for uploading the PC onto the stack. So here the PC, and that will be loaded onto the stack, and then the RST, that code will be taken on the data lines. Say you can see this diagram, this is the hardware required for taking generation of the RST5 code. Now as we have already discussed, the RST5 opcode is EF. So EF means 11101111, that is F, this is E. So this, there is a tri-state buffer, and here we have the plus 5 volt supply, and these are the inputs DI0 to DI7. These are the inputs to the buffer, and the INTA bar signal from microprocessor, that will be used as a enable. And when say this is active low and this is bubbled, so that means when it comes, it will enable the tri-state buffer. Now RST code is EF, already we have discussed. So if interrupt acknowledged by the microprocessor, then INTA signal will become low. Then RST is gated into the system bus. The RST5. RST5 means this is the code for RST5 EF. So that will be going, or it is gated into the system bus, that means the data bus. So it will enter to the data bus, and then the microprocessor saves the content of PC in the stack and jumps to the location 0028, because the table we have seen for that. If I go back, I think we'll be able to get it 0028. So RST5, the code is EF and the location is 0028. So it will go to this location. So, and the ISR will start and it will end with the return instruction. So when after the execution of return instruction, again the processor restores the saved address in the stack to PC, and normal execution of the main program will be started. So in this way, the non-vectored interrupt will have to generate the address with the help of the RST5 code. So here we have taken RST5 code, and the opcode for that is EF, and that is used for generation of address 0028. So with this, we come to the end of this video. If you have any questions, you can contact me on Facebook, Twitter, Gmail, Instagram, or website, or you can leave a comment on YouTube. Then if you like the video, press the like button, share with your friends, and subscribe to our channel Engineering and Technology for You. And don't forget to press the bell icon so that you get notifications for our future videos. Then thanks for watching. Have a nice day.